we're going to talk about 7 number systems. The first of which are the natural numbers. We'll just zip through these. Followed by the integers, followed by the rational numbers, the real numbers, the complex numbers, the quaternions, and the octonions. 7 number systems. They all build, actually. This is a system inside this, and this is inside this, and this is all the way up to here. So the natural numbers could not be simpler. 1, 2, 3, 4, 5, 6. They're natural, right? You start with this thumb and work your way through the fingers and toes and keep going. Next. N stands for natural. And they're also called whole numbers, counting numbers, and there's no end to it. If you think you've reached the end, add 1. Now, seemingly maybe not too interesting, but next. There's 3 kinds of natural numbers. There's 1, there's the primes, and there's composites. The 1, the unit, is unique. There's nothing else like it. In fact, it's all you need to get all the rest. You just keep adding 1, and you add enough 1s, you get to any of the other numbers. The primes, well, what's a prime? It's a number that's not 1. 1 is not a prime. And it's divisible by only 1 and itself. Some examples. 2, 3, 5, 7, and so on. These are the first few prime numbers. You pick any one, like 17. What's it divisible by? 1 and 17. Now, if it's not 1 and it's not prime, it's composite. And what that means is you can write it as a product of primes. By the way, 2 is the only even prime number. All the rest are odd. 6 is 2 times 3, 8 is 2 times 2 times 2, and so on. Next one. 1001 is 7 times 11 times 13. Remember that. You can stretch your friends. Okay, there's a fundamental theorem of arithmetic, where arithmetic basically here means operations on whole numbers. Any natural number except 1 can be uniquely represented as a product of primes. So, here's 30, it's 2 times 3 times 5. There's no other way to represent 30 as a product of primes. 819, a prime may appear more than once. 3 times 3, 3 is in here more than once. And by the way, when we say unique, in order to make them unique, you always order them from the smallest to the largest, and then it's unique. So if somebody comes along and says, well, you could write this as 13 times 3 times 3 times 7. Yes, we could, but if we order them, we have a unique representation. And then here's one where you have the factor 2, it appears 20 times. So 2 times 2 times 2, 20 times, is the unique way to represent this as a product of primes. So we can generate all of them from the primes. If you got the primes, you could get everything else. Multiply them together. Now, here's an interesting conjecture. Goldbach, let's see, put one more line, maybe, okay, that's good. Goldbach conjectured if you take any even number, all right, like 4, something greater than 2, or 6, or 8, that you can write it as the sum of 2 primes. Normally you sort of multiply primes. Adding them is a little different. Anyway, should be another line there. Yeah, here's some more. You pick any even number, and you can probably represent it as a sum of 2 primes, most of the time in more than one way. But this is called a conjecture. It is not a theorem. A theorem is something that's known to be true. It's been proven. This has not been proved. Goldbach, who lived way back, he conjectured it in 1742. So 269 years later, it's still an open question. Is it true? Is it a theorem or not? And nobody knows yet. However, don't mess around with any small numbers. If it's less than 10 to the 18th, it's known to be true. Of course, they use computers to figure that out. Computers and some theory. But you're going to have to, if it's false, it's going to be a really big number that'll show that it's false. And it's probably true. Okay, so maybe the natural numbers is not such a simple set. There's actually a number of other open questions about whole numbers that are very simply stated, and the answer is not known. And some of those questions were posed by the Greeks over 2,000 years ago. Okay, let's move on to the next number system, Z. Z, the integers. What are the integers? Well, if you start here with 1 and go up, that's the natural numbers. If you negate them all and throw in 0, you have the integers. Okay? Why is it called Z? It's the German word Zahl, which means number. And, yes. Okay, negative numbers, of course. What's the temperature? Okay. My oldest son, when he was about 8, got the concept of negative numbers very clearly because he had lived for a while where it was very cold, and every day he'd run out and look at the thermometer. And he knew when the thermometer got below 0, it was cold. So when he started learning about negative numbers, he just says, oh yeah, they're below 0 numbers. Okay. So let's look at this equation here. Don't get nervous if you don't like equations. This one's fairly friendly. We're just looking for some number, x. We're going to multiply it by itself and add it to itself, and we want to get a 6. We're not going to go through the grimy details. We're going to just try a 2. Well, if I square 2, I get a 4. If I add 2 to that, I get a 6. That means x equals 2 works. It's a solution. Let's try a negative 3. Negative 3 squared is what?
9.
9, and it's a positive 9. Remember, a negative times a negative is positive. So you get a positive 9, add in a negative 3, you get 6. So here we have two integers, 2 and minus 3, that satisfy this equation. In fact, there aren't any more. Now, the point of this is, if all we had was natural numbers, no negative numbers, we're not going to find this one, right? Because it's not even inside our number system. So we're going to see this motif happen more than once. We got an equation, we want to solve it. It turns out one or more of the solutions is not in our current number system, so you just make the system bigger. So that's why, one of the reasons why we've gone from natural numbers, all positive, to integers, where we have some negative ones, so we can solve more equations. Negative numbers. It took a long time for people to accept negative numbers as something real. In fact, René Descartes, the guy who invented Cartesian geometry and coordinate systems, said, this is a false. This solution is false or less than anything. Did not like those numbers. However, the thing is, you're trying to solve these equations, like we just looked at, and you find out, oh, if we had a negative number, it works. And so they sort of force themselves upon the world. So, we don't have any problem. They're true. They're real. No problem. All right, the next number system is the rational numbers. Now the notation here, it looks confusing, it's pretty simple, and excuse the euro sign in the middle, I'll tell you about that. What this says is, if the set, these squiggly brackets mean we're defining a set of objects. The set of objects consists of m and n, this symbol here. If you throw away one of those bars and get rid of the part that sticks past the curve, so you have something that looks like a little epsilon, that's a symbol that just means n is a member of this set. In other words, m and n are integers. And we know all about them now. So if you have any two integers, n is not 0, then if you form the quotient, m over n, and you do all possible quotients, you have the set of rational numbers. Now, by the way, this shows you where rational comes from. It has nothing to do with like, oh, rational, irrational, the way we usually think of it. It's just a ratio. Okay, this is a ratio. Now, this little symbol here is an example of the frustration of the modern computer. See, on my computer, this is a nice symbol of what it ought to be. But on Daniel's computer, there's some font missing, so it's something different. Just don't expect to find that in a math book.
What are you using that Euro sign for?
Well, you would find it in a math book if you were buying one in Europe. Okay, next. Oh, Q quotient. Now notice that when you look at the rational numbers, all the integers are there. Because if you just pick n to be 1, and pick m to be any integer, what's some integer divided by 1? It's the integer. So the rational numbers include the integers and the ratios of integers. Except, yes, don't ever try and hit a 0 as a denominator. You probably got your hand slapped in high school for this. And probably never got a good explanation for why. And I won't go into it now. Okay. And again, where do rational numbers come from? Let's look at the next equation. Let's say we have this equation. We want to find an x, so if we multiply it by 2 and add 3, we get 4. So we move the 3 over here, we're going to subtract. We get 2x equals 1, so x equals 1/2. This is the only solution to this equation. And it's another example of why we need a bigger number system. We got a simple little equation here, and if I say find a whole number x, or an integer x to solve this, well, no hope, there's no solution. But of course, 1/2 works. Okay. Now we'll look at the number line here for a minute. This is a nice graphical representation of a number system where you pick an infinite line, you pick some point on it, call it 0, you pick another point to the right and say that's 1, and now everything else follows. Right? We just, whatever that distance is, we keep repeating it in both directions. We get all the integers, positive ones here, negative here. This is an attempt to expand the line from 0 to 2 here. Then we start saying, oh, there's rational numbers in there, right? 1/2, 4/3, etc. And now we take the interval from 0 to 1 and look at it. We're gonna spend some time here. This is called the unit interval. It's of length 1. And we note, okay, keep going. What rational numbers appear in here? Well, 1/2, 1/4, 1. Those are all in there, right? What are these numbers, by the way?
Fractions.
Pardon?
Fraction.
They're fractions, but there's a pattern to them. It's got to be a computer program.
Yeah. Everything's half.
Yeah. This 1/4 is 1/2 of 1/2. 1/8 is 1/2 of
Everything is a
1/4.
half.
You multiply by 1/2 to get the next one.
Right.
The denominators are powers of 2. 2, 4, 8, 16, 32, etc. Okay, next. Here's some more fractions in there. What do these represent?
Ours is 3.
Denominators are all powers of 3. Next. Now it's easy. Denominators are powers of 5. So how many rational numbers are in there? I mean, we could keep, you
It
give
says
me
14.
any number, like we could go now and say it's 7, 1 7, 1 7 squared, etc. We can keep going. Let's go to the next slide. Between every 2 distinct rational numbers, there's another one. All right? Now, initially maybe that doesn't sound so exciting, but what it really means is there's an infinite number. In fact, between any 2 rationals, there's an infinite number of rationals. For example, if we have q less than r, if you add q and r and divide by 2, that's another rational that's exactly between q and r. And you can just keep doing that forever, as they say, and you'll never run out of numbers between q and r.
Can I ask you a question?
Yes.
Okay, I lost you on the first line for some reason. It's between every two distinct rational numbers.
Okay.
So can you explain that a little further?
Pick any 2 points on that number line. Distinct means they're different. Okay. And we're going to pick rational points. So you can write them as fractions. What that says is, between those 2 points, there's another rational number. And what this little formula is just tells you how to compute it exactly. You know, let's just try it. Let's say Q is 1/2 and R is 3/4. So what's the point halfway between them?
I think.
Let's see, 3/4 plus 2/4 is 5/4 divided by 2, 5/8. You know, if you look at your ruler and look at 1/2 and 3/4, you know, that's about right. Does that clear that up? Okay, but it's important to note that when you say, well, there is at least one rational number between any 2, that really means, when you look at the implications of that, there's an infinite number of them. So you pick some little teeny portion of the real line, no matter how small, infinite number of rational numbers in there. And this property is, the technical term for this property is dense. The rational numbers are dense. All right, new equation. X squared minus 2 equals 0. Aha! This is a nice equation. Because you look at that number line and you know that if in any segment of it there's an infinite number of rational numbers, there's rational numbers all over the place. You might not think to ask, well, are all the points on there, they represent rational numbers? The Greeks, for example, didn't think to ask that. It was clear to them that every number was rational. But let's proceed. We want to solve this equation. What do? We move the 2 over there, x squared equals 2. Take the square root. Square root of 2 is 1.41. Where does that end? How far out do we have to go before we have square root of 2 exactly?
There is none.
You can't go far enough. These digits go on forever. You know, which is not unusual. Think of 1/3. If you write 1/3 as a decimal, 0.33 goes on forever. In this case, there's not such a nice pattern as that. Now, so we ask ourselves, is the square root of 2 on our number line? Well, okay, let's move a little bit further in here. Here's our number line, and here's our unit interval. We're going to construct a square of side 1 here. And we're now going to ask, how big is x here? Well, look here. X is a right triangle with one leg is 1, the other leg is 1. Remember old Pythagoras' theorem? You must have learned that in high school. So hypotenuse squared is equal to the sum of the other 2 sides squared. So x squared equals 1 squared plus 1 squared. X squared equals 1 plus 1. X squared equals 2. So x equals the square root of 2.
Oops, sorry.
Oops, not yet.
What away?
So the distance from here to here is the square root of 2. So we're going to draw a circle with that radius. And what happens? That point then comes down to here. So right here, where that circle crosses the number line, is a point that corresponds to the square root of 2. All right, next. Well, if the number line consists solely of rational numbers, and the square root of 2 is on the number line, then the square root of 2 is rational. Is that logic? Okay? All right. But we don't know that the number line consists solely of rational numbers. Maybe there's something else there. So here's what we're going to have some facts now. Go ahead. If m is even, then it must be possible to write it as 2 times something. Think about it. What's the definition of an even number? It's divisible by 2. If it's divisible by 2, you can write it as 2 times something. If it's an odd number, then you can write it as 2 times something plus 1. That plus 1, the 2 times something gives you something even. You add the plus 1, you have something odd. Now, here's a bunch of facts that we could prove, but we're not going to bother. If you have an even integer and another one and you multiply them, the result is even. No big surprise. You have a factor of 2 here and a factor of 2 here. You multiply. Wait a minute. We have a factor of 2 and then anything. We multiply, we still have a factor of 2. That was a quick proof, by the way. An odd integer times an odd integer is odd. That's a proof left to the reader. Next. Now, if you have a square and it's even, then you must have started with a square. If m squared is even, then m is even. Okay, we're going to prove a theorem here. Don't get nervous. A proof is simply an argument. We're going to show that square root of 2 cannot possibly be rational. Well, the approach we're going to use is, I think there was a famous mathematician once, I think Hardy, who said, in chess you might have a gambit where you give away a pawn to gain an advantage. He says in a proof like we're going to do here, a proof by contradiction, says you give away the whole game right at the beginning. So we start out and say, well, let's say we want to prove it's not rational. Let's say it is rational. Let's see where we go. Well, if it's rational, what's that mean? It's a ratio of 2 integers. So we can write it as m over n. And we can make sure that m and n have no common divisor. If there's a common divisor, divide out. So you end up with a ratio where m and n have no common divisors. Okay. Now, we're going to take this equation, square both sides. Square that, square that. What's the square of the square root of 2? 2. Squaring and square rooting are inverses. So the square root of 2 squared is 2. This is m squared over n squared. Now we're going to multiply both sides by m squared to get to 2n squared equals m squared. Now let's back up a second. Now what does that tell us about m squared?
M squared is even.
It's even because it's got a factor of 2. Okay. And here we say that. M squared is even, so m is even. So that means we can write m as 2 times something. So we've learned something about m. Keep going. But now, wait a minute. You know what? Let's back up a little bit. I want to be real clear where we're going here. Back up to the previous slide. Okay, we're at this position here. 2n squared equals m squared. And m is 2q. So, we're going to write 2n squared equals, well, m is 2q, so put 2q in here, square it. So 2n squared equals, that's 4q squared. Divide the 2 out of each side, so n squared equals 2q squared. What's that tell us about n squared? N squared is an even number, and since n squared is even, n is even. So now we have n equals 2 times something. So what do we got here? N equals 2 times something, and m equals 2 times something. But remember we started out and said there's no common divisor. So what did we arrive at here? Yeah, but we started out and said they didn't have one, but we proved they do have one. So what's that mean? What our assumption was, we can write the square root of 2 as the ratio of 2 integers. By assuming that, we've arrived at a contradiction. That means our assumption's false. So the square root of 2 is not a rational number. Okay. Yeah, I just said that. Here's another example of a missing font. That's supposed to be a little square completely filled in with black, which is a modern way to show the end of a proof. The old-fashioned way to show the end of a proof was QED, quod erat demonstrandum, that which was to be demonstrated. So, if it's not rational, what is it? It's irrational. Now, this is what a non-mathematical usage is of irrational. Not endowed with reason, incoherent, marked by a lack of accord with reason or sound judgment, which is the way a lot of people think their high school math courses. But all it means is that it's not rational. In other words, it's not a ratio of 2 integers. So an irrational number is not a number that refuses to be reasonable. It's simply a number that's not a ratio of two integers. Now, the ancient Greeks discovered that square root of 2 was irrational, and they discovered there were a lot of different ones. In fact, there's a proof in Euclid's Elements, although it was known before Euclid. Now, it created a huge crisis in the world of Greek mathematics, because up until the discovery that the square root of 2 was irrational, there had been an implicit assumption that obviously all numbers are rational. And they realized, as soon as they saw there was something, a number that wasn't rational, they realized, well, maybe all of our proofs are no good anymore, because we've made this basic assumption. Now, they were able to recover. They figured out ways to make their proofs work anyway. And there's a lot of interesting stories about how, when this was first discovered, the discoverer and everyone around him was sworn to total secrecy. Don't ever let anybody know the square root of 2 is not rational, etc. But nobody really knows. But it makes a good story.
Didn't they send someone out on a boat and burn them to death first?
Well, there's a story that one guy blabbed, and he jumped on a boat to escape, and the boat sank or something. He was punished.
Yeah.
Nobody knows. It's just all, it's old Greek stories. So other irrational numbers. Let's take a look at what we've got here. If you pick any natural number that's not a perfect square, its square root is irrational. So 3, 5, 6, 7. Square root of 9 is 3, so it's okay. But any natural number which is not a perfect square, its square root is irrational.
Say what a perfect square is again? What is it?
Perfect square is a number like 4, 9, 16. It's an integer. It's a whole number, which is
Integer times
which you
itself.
take the square root of and get another whole number. Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4, etc. Now, the cube root of any natural number that is not a perfect cube is also irrational. There's tons more. For example, pi, the ratio of the circumference of a circle to its diameter. I had a nice little Greek symbol in there, but it wasn't on this machine. Okay. All right, so we got this number line. We know there's infinite number of rational numbers in there. We know there's a few irrational numbers in there. What we're going to do is we're going to say, hey, every number on that line that's irrational and every one that's rational, we're going to lump them together into a set we're going to call the real numbers. And here's a fairly lame definition. The real numbers are the rational numbers union or combined with the irrationals. Now, why the term real? We won't understand that until we get to imaginary numbers, so we'll get to that in a little while. Now, my definition of real numbers has kind of avoided some really interesting things that we don't have any time to go into here. You can't really define what the real numbers are without the concept of a limit. And if any of you ever had calculus and got into limits, we're not going to go into limits here. And also the real numbers are very subtle. We won't go into that too much either. But here's something that's surprising if you think about it. The real numbers weren't even properly defined until 1880, roughly. Okay? You remember Newton and those guys? They were busy doing stuff in the late 1600s, inventing calculus and figuring all that stuff out. And they just, for 200 years, all kinds of things were being discovered and worked out. And yet, the fundamental set of elements that they were using, the real numbers, weren't even adequately defined. Which goes to show you that sometimes your ignorance can save you. Okay, by the way, now the number line's complete. There's nothing else on that line except real numbers. Every point on the line corresponds to one and only one real number, vice versa. Okay, we'll call it the real line. All right, so with real numbers, we can solve that equation, x squared equals 2, which we couldn't before. And now let's just pause and look at the number systems we've dealt with here. The natural numbers, the integers, the rational numbers, and the reals. And consider, can we add, yeah, we can add those, any of those. You add two natural numbers, you get another one. Multiply, no problem. Subtract, subtraction, when you only have positive numbers, doesn't work too well. If somebody says, tell me what 4 minus 8 is. Well, the answer is minus 4, but if you're working with positive numbers, there is no minus 4. But in these other systems, you can subtract. Division. Well, what's 7 divided by 3? 7 divided, well, it's a perfectly fine rational number, but it's certainly not a whole number. So you can't really divide here. What about taking roots? Well, taking roots of something like, well, 2, take the root of 2, you don't get any one of these, you get one of these. So you can finally take roots. This is another example here of how the number systems grew in order to make it possible to do more and more stuff. Okay. So here's an example. This is just showing that each one of these sets is essentially a proper subset of the next one up. So if you look at the real numbers, inside them are the rationals. Every rational is a real number. Every integer is a rational and a real number, and every natural number is an integer and a rational and a real. So we're just basically, the number system's growing. Okay, what's next? It's break time. After which, we're going to move on to complex numbers. And then we're going to move on to even more complex. All right, part 2. Oh, okay, yes, we're going to look at properties that number systems can have. For example, all the number systems we've looked at are ordered sets. You can talk about one number is less than another. Keep going. Oh, yeah, we're just running through some things. We're going to look at commutative laws, associative laws, distributive law. Go.
Whoop, whoop.
Is that supposed to be commutative?
Commutative. As in commuting. They commute. We'll see examples in a second.
We move ahead?
Yes. Okay. If you got any A and B are any two real numbers, then exactly one of the following three things is true. A is less than B, A is equal to B, or A is greater than B. All right? And this is true for any two real numbers. The real numbers are an ordered set. And if you pick any subset, it's ordered too. For example, this subset's ordered, this subset's ordered, and this subset's ordered. And the whole set's ordered. Now, what's a commutative law? Addition is commutative. It simply means when you add A and B, it doesn't matter what you add. A plus B is equal to B plus A. Example, 3 plus 4 equals 4 plus 3 equals 7. I know some of you are saying, what is this obvious stuff all about? That's what I want to say. Keep going. Multiplication is commutative. A times B is equal to B times A. Doesn't matter which order you multiply in. Okay. Associative. Addition is associative, which means if you're going to add three things, you can either add the first two and then add to the third, or you can add the last two and then add that one in. 3 plus 5 plus 2 is the same as 3 plus 5 plus 2 is 10. Multiplication is associative. Getting boring, right? Okay, a little distributive law. Multiplication distributes over addition. If you multiply A times a sum, it's the same as multiplying A times each of the components of the sum and then adding. This stuff, we don't even think about this stuff because it's, it's ingrained in us from the time we start doing arithmetic. So why do we want to talk about it? Because. Next. Keep going. Okay, we haven't, okay, I don't know where the slide, here's the reason we're going to talk about it. Because these rules, some of these laws are not going to hold in other number systems. They break down. In all of these sets we've seen so far, they're all ordered. Addition and multiplication are commutative and associative in all of them, and multiplication distributes over addition. But, yeah, what's the big deal? Because we're about to arrive at some systems where these laws don't hold. Another equation, x squared minus 1 equals 0. Let's solve it. Move the 1 across to here. X squared equals 1. X equals square root of 1. Hold it.
Whoop.
No, that was too hard. You've already seen the answer. Go ahead. There's two answers here. X is 1 and X is minus 1. Because 1 times 1 is 1. Well, plug a 1 in here. 1 times 1 is 1, minus 1 is 0. Plug a minus 1 in here. Minus 1 times a minus 1 is a 1, minus a 1 is a 0. So those are the two roots for that equation. The term root, by the way, root means solution. And here's where we check our results. It all holds together. And remember in high school, this was drilled into you, I would hope. And maybe even explained.
Is there an explanation for that?
Yeah, there is. You know? But just take it on faith. No. Next. Now, this equation is slightly different. We changed the minus sign to a plus sign. Let's see what happens when we try and solve it. Okay. Okay, hold it a minute. X is equal to square root of minus 1. So what do you think X is?
Plus or minus.
What's X?
Alright, what is this for?
Imaginary.
Somebody says there is no square root of minus 1. Somebody else says I, as in the little letter I. Well, let's take a look here. Well, yeah, we don't know. Here's the problem. We want a number such that when you multiply it by itself, you get a minus 1. But negative times a negative is positive, and a positive times a positive is positive. So we are just not going to find a real number which when multiplied by itself gives you a minus 1. There just aren't any. They don't exist. Can't possibly be one among the reals. Keep going. So,
Whoops.
just, it's sort of like, hey, you know, sweep that under the rug, forget about it. It's uncomfortable. However, I mean, and that was, you know, a definite way to approach it, and people did that. Here's what people said. It's an imaginary number. It doesn't even exist. But here's what happens. 16th century. Let's move forward a little bit. Okay, we need some notation. Oh, the notation is, it's awkward to write square root of minus 1, so a man named Euler in the 1700s said, I'm going to call it little I. And it's been called that ever since. Except, next, used universally among mathematicians, but electrical engineers call it J. Because they use I for something else. We have electrical engineer in the back who can tell you all about it, but we won't go there. Okay. Yeah, and in a while we're going to get to J being used as another kind of imaginary thing, so then we're really in trouble if we're dealing with electrical engineers. All right, let's look at this equation. We want to find a number x such that we want to find a number x, and then of course once we know x, we know 4 minus x. So what we have is that the product of this and this is 5, and the sum x plus 4 minus x is 4. So we're looking for a number that we're looking for two numbers in a sense that add up to be 4 and when multiplied together give a 5. So let's see what we can do here. Yeah, split it into two parts. Split 4 into two parts. The sum is 4. This product is 5. Now, we're not going to go through the grimy details, but if you remember your quadratic equation from high school, you can do this. Now, what you end up with is you end up with 2 plus I. Remember, I is the square root of minus 1. And 2 minus I. Which, you know, you thought I was bad. Well, now we're adding things to it. But let's just see what happens. If we add this and this, 2 plus 2 is 4, and I plus minus I is 0. So the sum of those two numbers is 4. Remember, we're looking for something The sum is 4. And let's see what the product is. Okay, 2 plus I times this, distributive law. 2 plus I times 2 plus 2 plus I times minus I. Let's go a little further. This is 2 plus 2I. This is minus 2I minus I squared. The 2I and the minus 2I cancel, so we're left with 4 minus I squared. Well, what's I? Square root of minus 1. So when you square it, what do you get? Minus 1. So I squared is minus 1. So now we have 4 minus a minus 1 equal to 4 plus 1, which is 5, which is what we wanted. So this tells us, here's a couple things this tells us. There is a solution X to this problem. It involves something that has the square root of minus 1 in it. But if you just do your arithmetic in the normal old way, multiply, subtract, divide, and everything, and just remember that whenever you see an I squared, make it minus 1, everything kind of works out. Now, this was one of those fellows back in the 16th century, putting aside the mental tortures involved. Multiply 2 plus I by 2 minus I, making 4 minus a minus 1 equals 5. This is truly sophisticated. He was in the process of trying to figure out how to solve cubic and quartic equations, and these pesky, quote, imaginary numbers kept cropping up. And it was like, everybody kind of wanted to ignore them. You couldn't quite ignore them. And he was noticing, well, just keep working with them like they were ordinary old numbers, and things kind of work out. But are they real? This is the fellow who invented logarithms. He called them ghosts of real numbers. Descartes was the first one who called them imaginary, and he was a derogatory use of the word. They aren't real, they're imaginary. And here's where the term real came in. It was like you want to distinguish the real thing from those imaginary things. Okay. Remember that song? Okay, when you do arithmetic with numbers involving I, you always end up with something that looks like this. A real number plus a real number times I. So no matter how complicated you get and how many exponents and everything else, ultimately, in a certain sense, you end up with something kind of simple. A real number plus a real number times I. And these are called complex. And it has a real part, B, and it has an imaginary part, C. Now really, probably these numbers should have been called something like compound, but they were called complex. Now, if B is 0, if that's a 0, then you just have a number like Ci, which is a real times I. And these are called pure imaginary. There's no real part. Okay, so here we have a definition of what are the complex numbers. It's a set consisting of things which look like B plus Ci, where B and I are, ignore the euro sign, real. B and C.
B and C.
B and C, pardon. And I is square root minus 1. Okay, keep going. Now, you can think of the complex numbers as a pair of real numbers, because if you give me two real numbers, and give me the order, B and C, then I can form a complex number by writing B plus Ci. So C is two-dimensional, which was noted by the following people: Bessel, Argand, and Gauss. All of these people are given credit for what we're about to see next, which is a way to visualize complex numbers. Here's our friend, the real line. All right, here is an imaginary line, which looks just like this one, but it's turned at a 90-degree angle. And notice we have I, 2I, minus 2I, etc. So if you pick any point on this, it's a purely imaginary number. If you pick any point down here, it's real. And if you pick a point in the plane, well, you look at what's the real part, 2. What's the imaginary part, I. So that point represents the number 2 plus I. So this graphical representation was a big breakthrough because now all of a sudden it's like, hey, what do you mean imaginary complex? It's pretty simple. We take the plane and we pick points in the plane, and those points correspond to complex numbers. Just like the points on this line correspond to the real numbers, the real number line, we now have the complex plane. People felt a lot more comfortable when they could draw pictures of things. Okay, a property that C has is that it's algebraically closed, which means, oh, by the way, one thing about identifying the complex numbers with the points in the plane, if you're just doing your normal Cartesian geometry, analytic geometry, drawing graphs and stuff, there's one thing you never really do, and that is you don't ever multiply 2 points together. You could maybe add them, subtract them, but you don't really multiply them. The complex numbers, with the complex numbers, the points in the plane correspond to the complex numbers, and you have a multiplication operation. So given any 2 points in the plane, you can multiply them. And exactly what that means, see me after the talk and I'll tell you. Okay, let's go a little further. Now here, okay, yeah, keep going. Here's a polynomial equation. Okay, quadratics, all these equations that you had in high school. You have an unknown, in this case it's z. You have some highest power, in this case it's a 4. So this is called a quartic equation. And then you might have a power 3, power 2, power 1, power 0, and you have various coefficients. In the world of complex numbers, there's always a solution to such a thing that is a complex number. That's what we mean by algebraically closed. If you given any polynomial, and the coefficients, by the way, could be complex numbers, they don't have to be real, you're guaranteed to have a solution. And by the way, once you've got one solution, you're guaranteed to have, in this case, 4 solutions. Some of them may be the same value. So, we don't have to look for any bigger number systems in order to solve equations because we can solve them all in the complex numbers. Remember the various things we talked about? These sets are ordered in their commutative. Well, the complex numbers are not ordered. You know, think about it. You got a point here and a point there. Which one's bigger than the other one? Doesn't make sense. There's no ordering for complex numbers. You can add, subtract, multiply, and divide and take roots. All of these laws that we've looked at, commutative, associative, and distributive, all hold. But it's not ordered. Keep going. We've already said all this. Now, these terms, real, imaginary, complex, etc., they're just technical terms in math. They have very precise definitions, and you don't really want to confuse them with everyday use of these terms.
Question?
Yes?
With your complex numbers, you're in a plane, and you can talk about the radius out to that plane. That's ordered, is it not?
Well, but let's say, yeah, draw a circle of radius 1. Pick 2 points on that circle, which is bigger than the other.
Oh, in that case, they're both the same.
But they're not equal. The numbers are not equal, right? If I pick one on the left side, one on the right side, they're not the same number. So you can't, it just doesn't work to try and get an ordering like the ordering on real numbers. Okay. All right, let's keep going. All right. So one thing about the complex numbers, the complex plane, is, well, remember I mentioned electrical engineers use complex numbers? Complex numbers are a powerful tool for doing engineering, for doing science, and so on. But of course, you're dealing in a plane. So a natural question is, well, hey, what if we had a 3-dimensional number system? Because then we could have a powerful way to model things in 3 dimensions. So an Irishman, William Rowan Hamilton, Spent 15 years looking for such a system. Now, what he didn't know was, well, here's what he wanted to do. He says, look, I want to get one more imaginary unit, j. And I want I squared equal minus 1 and j squared equal minus 1, but I and j are different. And then I want my numbers to look like this. A real number plus a real number times I plus a real number times j, with all those things real. So you can see what he's doing. He's generalizing. A complex number, you take two reals. He says, let's take three reals. But you can't just say, oh, there it is. You got to just define, okay, how does multiplication work? How does addition work? And he could never get it to work out. He wants all the usual laws to hold. Now, what happened? The reason he couldn't get it to work out is such a beast does not exist. And you can prove that. However, if you say, you know what, not just an I and a j, throw in a k, then you can get a system. Here you have B, C, D, and A, and you have I, J, and K as imaginary units. And you have a four-dimensional system, and
Wow.
all of the laws of all the arithmetic laws work except for one, which we'll look at in a minute. So Hamilton called these things quaternions. You know, you can see quat. There's a 4 in there, right? Something that consists of 4 real numbers. They're denoted H in honor of Hamilton. Now, I squared, J squared, K squared, and the product I, J, K are all minus 1. This is very important for helping to when you're trying to do arithmetic to see what things end up being. Okay, keep going. I've already said all this. Yeah, and you can think of a quaternion as it's a quadruple of real numbers. You got 4 of them here. Now,
Excuse me?
yes,
Can you explain how that ijk is equal to minus 1?
Yeah.
by definition. Okay. In other words, in the complex numbers, we have this thing called an I, and it's not a real number, it's something in addition, and we say this thing has the property that when you square it, you get a minus 1. Now, once you do that, once you take, here's the real number line, and you throw in one thing that doesn't belong on it, and you define it as by saying its square is a minus 1, bingo! That generates all the complex numbers. And all the arithmetic and everything else can be derived from that. Now, what Hamilton did is he said, okay, that's neat, but I'm going to take it further. I'm going to have, in addition to I, I'm going to have 2 more things that aren't real numbers. I'm going to have a J and a K. They have the property that when they're squared you get a minus 1. And they also have, can we back up, please? He also said, and I want the product of I, J, and K to be a minus 1. Now, from these 4 conditions, I squared is minus 1, J squared is minus 1, K squared is minus 1, and this product's minus 1, you end up with a system in which you can add, subtract, multiply, and divide. All the usual laws hold except one, which we're about to get to. Let's see. If I, J, and K are minus 1, let's multiply both sides by K.
Yeah.
So then we have ij k squared is equal to minus k. K squared is a minus 1. So we have minus ij equals minus k. Ij equals k. I times j equals k. Now what I just did there, by the way, these conditions imply that ij equals k. I just went through a brief derivation that was the case. But it all came from these conditions and using the usual rules of arithmetic. In fact, now you mention that, I'm pretty sure that ij is k, jk is I, and ki is j. I think it's circular. A nice little story about Hamilton's flash of insight when he realized he had to have 3 imaginary units. He writes, on the 16th of October, 1843, as I was walking with Lady Hamilton to Dublin and came up to Broom Bridge, I then and there felt the galvanic circuit of thought close, and the sparks which fell from it were the fundamental equations between I, J, K, exactly such as I have used them ever since. Nor could I resist the impulse, unphilosophical as it may have been, to cut with a knife on a stone of Broom Bridge the fundamental formula with the symbols I, J, K. Now, that carving's gone, but, okay, let's see what doesn't work. Well, what works in a different way. From these relationships, it's fairly easy to do so. Here's an example. Yeah, so J, yeah, okay, we won't go any further. But here's what's unpleasant about this. I times J is not equal to J times I. Now that's new. Multiplication is non-commutative.
Is not equal to?
Not equal to minus.
Minus.
Yeah.
It is equal to minus
Yeah.
data.
Yeah, I should say, take away the minus and put a not.
Yeah.
Well, or just IJ is not equal to JI.
Okay.
Did I say it right? Okay.
Yeah.
Which, think about it. 3 times 4 is equal to 4 times 3. But I times J is not equal to J times I. So this, in fact, this was initially a big stumbling block. It was like, well, hey, if it's non-commutative, this must be garbage. But it turned out, in fact, these quaternions were a big deal. They worked really nicely for a lot of things. And it expanded mathematicians' worldview to go beyond the existing laws they were familiar with the old number systems. It's like, hey, so things don't have to be commutative. Some are, some aren't. Okay. Now, they are 4-dimensional. Quaternions are 4-dimensional, but it turns out they can be used to model things in 3 dimensions.
When you say they're 4-dimensional, do they form a plane in 4-dimensional space?
Well, think of it this way. Just like a complex number is a real plus a real times I, and that means that you can represent it as a point in a plane. A quaternion can be represented as a point in 4-dimensional space. So the B, C, D, E, or whatever, the 4 real values. It's like, okay, go up on the x-axis this far, and the y-axis this far, and the z-axis this far, and then it gets hard to visualize. But you just go out on the 4th axis so far, and you got a point in 4-dimensional space. So there's a one-to-one correspondence between the quaternions and 4-dimensional space. Okay. Yeah, if you don't look at the real part, and you just look at this part, this looks an awful lot like a 3-dimensional vector. Now, vectors hadn't been invented yet, right? But they were invented pretty quick, and there was this big fight between the quaternion types and the vector types over what's the best way to represent physical reality, blah, blah, blah. Quaternions lost. You've never heard of them, right? But
They're coming back.
they're back. Because it turns out quaternions are a really slick way to represent rotations in 3-dimensional space. And in particular, where is it that rotations in 3-dimensional space play a big role in our lives now?
Flying.
Computer graphics, right? You see all these images, they create these worlds that don't exist, but they look real. Well, there's a whole lot of stuff going on in 3-dimensional space there, and a lot of it's being represented by quaternions inside the computers.
Yeah.
So they're back now, and you can buy entire books about them. Okay, next. Now, if you ever get to Dublin, you've heard of June, I think it's June 16th. Every June 16th, Bloomsday, there's a walk. You can go to Dublin and you can take a walk following the path of the hero of the book Ulysses by James Joyce. That book takes place in a 24-hour period, and people from all over the world arrive in Dublin on the 16th of June in order to take this walk that the book is about. Well, there's another walk that you never heard of. It's on October 16th, And very few people, mathematicians, gather and take the walk that Hamilton took. Oh, by the way, I think this is the modern spelling of this bridge. And don't let that confuse you. The scratchings are gone, but they put up a plaque. Here's what it says. Here as he walked by on the 16th of October, 1843, Sir William Rowan Hamilton, in a flash of genius, discovered the fundamental formula for quaternion multiplication and cut it on a stone with this bridge. Go to Wikipedia and look up Broom Bridge and you'll see a photo of the plaque and everything else. Now, hey, we got quaternions, 4. Why stop? One thing mathematicians do is they generalize. They take, oh, 1, 2, 3, 4, let's go higher. And it turns out you can go a little higher. But you can't get a decent number system of dimension 5, 6, or 7. However, 8. We need 4 more units. I, J, and K. How about uppercase E, I, J, and K? Throw in 4 more units. This was two guys figured this out. This guy actually figured it out first, not long after Hamilton invented quaternions. But Cayley came along in between, and Cayley gets the credit for it these days mostly. And what did they come up with? Octonions. 8 dimensions. See this? You need 8 real numbers to specify 1 octonion. And you have 7 imaginary units. Okay. And to rigorously define exactly how things work, you need a 49-element multiplication table. You've got to list the 7 imaginary units this way, and then show for each pair, if you multiply them, what do you get? Now, multiplication is non-associative. This is really wild. This means if I multiply I and j and then multiply the result times z, I don't get the same thing as if I multiply j times z and then multiply that by I. So, you know, with quaternions, we lost commutativity in multiplication. Now we're losing associativity. We're kind of running downhill in a certain way here. Okay, next. However, in technical language, the octonions is a real division algebra, which is what R, C, and H are. Algebra here is used in a technical sense. It describes a set that has certain properties. 8-dimensional, and guess what? These are the only ones that are associative. Okay? This is the only one that's non-associative, and there aren't any more. Yeah, go ahead and fill this out here. All of these gentlemen were involved in, whoops, go back. All of these gentlemen were involved in proving that these are the only finite dimensional division algebras that there are. There cannot be any others. And here again we see the relationship between these things. The real numbers are a subset of the complex, a subset of the quaternions, a subset of the octonions. So, John Baez, who is,
Not Jones.
I think he's a cousin of John Baez. Yeah, I believe so. I think he's at Stanford. We're going to conclude here with his sort of summary of how to think about these systems. The real numbers are the dependable breadwinner of the family, the complete ordered field we all rely on. The complex numbers are a slightly flashier but still respectable younger brother, not ordered but algebraically complete. The quaternions, being non-commutative, are the eccentric cousin who is shunned at important family dinners. But the octonions are the crazy old uncle nobody lets out of the non-associative. One more. So there they are. 7 number systems.